Alkalinity supplements. One of the most common issues that reef keepers face involves supplementing alkalinity while maintaining a reasonable pH. Alkalinity supplements impact pH in a variety of ways. One of these ways is the immediate altering of the pH. Different alkalinity supplements have different immediate impacts on pH, as most reef keepers are aware. This impact is why, for example, lime water needs to be added slowly to a tank, but sodium bicarbonate does not. For this discussion, let's presume that we want to supplement the carbonate alkalinity of a reef tank. That is, in the end, we want to increase the bicarbonate and carbonate levels in the tank. There are a variety of ways to achieve this end, and these different ways have different immediate impacts on pH. Three of these ways and combination thereof are fairly common in reef keepings. These ways are additional of bicarbonate, carbonate, and hydroxide. In a reef tank that is permitted to equilibrate its total CO2 level with the atmosphere, these additions all end up with the same final pH. That is, it is only the amount of alkalinity added that determines the final pH, not the nature of the additive itself. In short term, however, the impact on pH is very different. To quantify this, I measured the pH change on adding 0.5 MEq per liter of each of these alkalinity supplements to freshly made salt water. Instant Ocean made to S35, alkalinity measured to be 2.26 MEq per liter by titration. Here's the result of the pH found immediately, and then after 24 and 120 hours of sitting unstirred in an open 500 ml beaker. Okay. From this data, it is clear to see the large increase in pH caused by the addition of hydroxide. It's clear to see the large increase in pH caused by the addition of hydroxide, which is this. Which is this in short term. And also the significant increase when using carbonate, which is this. Yeah, see the increase? Yes. Bicarbonate, on the other hand, shows the expected slight decrease in pH, but not nearly as much as found with a strong acid of equal concentration, which is bicarbonate. So it drops actually, okay, and acid expectedly drops. It is also clear that after sufficient time to equilibrate with atmospheric CO2, okay, so it's leave them for 24 hours and 220 hours, pH is changing along the time, changing with the time, because of atmospheric CO2 stirring with it. These differences disappear and the pH is the same for all of the 0.5 MEQ per liter alkalinity addition. This is an important result in seawater in equilibrium with the atmosphere. For a given alkalinity, there's a single pH that results regardless of what was added to get to that alkalinity. So we can see this is the initial. So water is this. Okay, so this is seawater, which is made by this. So without adding anything, is this. Adding bicarbonate is a drop. Then when time goes by, with the factoring of atmospheric CO2, it increases, start to increase. Adding bicarbonate, a huge increase in pH initially, and slowly it drops and come up again. Interesting. Base. So when base is meaning pH increase, but most likely increase the pH in short term is okay, is expected, and after a few time, after period of time, it drops, start dropping. Exit, which is basically pH down, sort of, it drops and slowly increase. So what we can see is atmospheric CO2 is quite huge. It's amazing the thing that these things will do to the pH. Here's how to think of this addition. When these chemicals are added to the water, there is a change in the relative concentrations of carbonate and bicarbonate. There is a change in the relative concentrations of carbonate and bicarbonate, and it is the ratio of these two ions that determines the pH. Hydroxide addition. For hydroxide addition, the first thing that happens is that bicarbonate is converted into carbonate. So bicarbonate, addition of hydroxide, which is base, more carbonate, so it's converted as shown here, and the small amount of carbonic acid present is converted into bicarbonate, and the small amount of carbonic acid present is converted into bicarbonate. So with this happens these two things. So bicarbonate is converted to carbonate, and carbonic acid reacting with hydroxide is converted to bicarbonate. So it will convert to bicarbonate and water. It becomes this. The net effect is that the pH rise that is normally encountered by adding hydroxide to water is reduced. The net effect is that the pH rise that is normally encountered by adding hydroxide to water is reduced. Okay, because it happens when bicarbonate react with hydroxide, more carbonate. And when at the same time carbonic acid react with this and this. For example, adding 0.5 MEQ liter of hydroxide of fresh water will drive the pH into the 10th. What's that? In seawater, the pH rises much less and the conversion of bicarbonate to carbonate is largely responsible. The pH rises much less, and the conversion of, okay, so this is responsible for this. Let's read on. In this situation, the tank is now deficient in H2CO3, which is carbonic acid, because the small equilibrium amount of carbonic acid normally present was partially converted to carbonate by the base addition, and the tank proceed to absorb CO2 from the air, bring the pH down a bit by releasing H2, H plus. So H plus, more H plus will bring down pH. There are many ways to show this reaction, but the net process involves CO2 from the air becoming carbonic acid. But the net process involves CO2 from the air becoming carbonic acid, and the carbonic acid deprotonating to carbonate. What is this deprotonating? Okay, deprotonating is to remove a proton, sometimes written as does not refer to the eject. Deprotonation does not refer to the ejection of removal of hydride ion. The removal of hydrogen radical is termed hydrogen extraction, so it's different thing. Is it something like that? And some of the bicarbonate deprotonating to carbonate. CO2, atmosphere CO2 plus water reacting with water will become carbonic acid. Carbonic acid will become bicarbonate plus H plus, which is hydrogen. Hydrogen will tend to bring down pH. More hydrogen, carbonate, bicarbonate, then from here bicarbonate will react again and become carbonate plus H plus, H hydrogen. Air becoming carbonic acid. The carbonic acid to carbonate, and okay. In this extent, that's deficient in carbonic acid because normally present converted to by H addition, and the tank absorbs CO2 from the air, bringing pH down by a bit by releasing H plus. Yes, so it is lowering. Why is it lowering pH? So this is why it's lowering pH. So in the experiment, when when they add in what I'm confused. But where's the linkage? What the fuck is he talking about? Okay, let's skip for a while. Let's skip for now. We will come back when we will come back when we organize the thought again. The reactions taking place in equation 11 to 13 all serve to lower the pH, which is correct, which I mean more hydrogen will decrease the pH, all serve to lower the pH from 2 in the experiment above. Okay. When equilibrium is reached, however, the pH has not dropped all the way back to the point before the hydroxide was added. But it is slightly elevated. When all is said and done and the tank has fully equilibrated with the air, the hydroxide addition has caused the tank to experience an increase in bicarbonate and carbonate and in pH. So this is base, which is hydroxide. So hydroxide addition so they say everything. They never say exit though, but it's okay. Let's go ahead to carbonate addition. The case for carbonate addition is similar to that for hydroxide. In this situation, the pH rises because much of the carbonate combines with H plus to form bicarbonate. Sorry. This obviously reduces the H plus, which result in a higher pH. The case for carbonate addition is similar to that for hydroxide. In this situation, the pH rises because much of the carbonate combines with H plus to form bicarbonate. This obviously reduces the H plus, which result in higher pH because absorb more this result in higher pH. When this is released more, it will lower down pH. So H plus carbonate added more bicarbonate because it absorbed to become bicarbonate, pH lower. In this case, the net short-term effect is that carbonate and bicarbonate increase and the pH rises from 8.1 to 8.44 in the experiment above. So carbonate increase, slowly reduce. 8.44. Yes, 8.44, correct. In the long term, the higher pH causes more CO2 to be put in from air, as was the case with hydroxide additions. This limits the pH rise and further increases the bicarbonate concentration. Still, the end effect is the same as hydroxide addition. The tank experiences an increase in bicarbonate and carbonate and pH. Yes. So they increase, both of them increase, and with the disturbance of CO2 atmospheric, they do this. Lower. Okay, bicarbonate addition. The addition of bicarbonate as an alkalinity supplement is rather different. In this case, the bicarbonate partially dissociate into carbonate and H plus, and the tank experiences an increase in bicarbonate and carbonate and drop in pH. So increases of this one is added, this went up because it disassociates, so more hydrogen is released into the water and more carbonate into the water. Consequently, the immediate effect on pH is for it to drop. Yes, the drop is small because not much of the bicarbonate dissociates at the normal 10 pH, but enough thus to drive the pH a bit lower. Okay, correct. In the long term, however, the effect is different. Since a substantial amount of bicarbonate was added and the pH did not change much, the tank is now overloaded with bicarbonate with respect to what it would normally have in equilibrium with air. Some of the bicarbonate picks up a proton, becomes carbonic acid, and the pH rises as the CO2 is blown off the atmosphere to the atmosphere. So bicarbonate plus hydrogen, it is taking out hydrogen from the water, which increase the pH and become acid. Then when carbonic acid and carbonic acid is inside the water, is very reactive. So because more CO2 is in the atmosphere, then the ratio of the CO2 level in the water and atmosphere is different, which means CO2 in water is more and atmosphere CO2 is lesser. It tends to gas off. So CO2 gas off, leaving only water. So bicarbonate this is how it works. In the experiment above, the effect has caused the pH to rise from 8.06 to 8.33. So the long-term effect of bicarbonate addition, as it is for an addition to carbonate alkalinity, is to rise pH, even though the short-term effect was to lower it. Summary: alkalinity and pH are two of what I would call the big five in terms of parameter important in keeping a reef tank, the others being calcium, salinity, and temperature. Alkalinity and pH are related to each other in ways that are obvious, and in other ways they are much more subtle. Unfortunately, these parameters are often problematic for people maintaining aquaria, and the relationship between the two is one of the biggest areas of concern. I have found that more than half of the questions posed on reef chemistry internet forums relate to pH and alkalinity. Obviously, these parameters are confusing to many aquarists. Hopefully, this article has put this relationship in perspective and will help aquarists to better understand their systems. Okay, so through this article we understand the relationship between these two parameters, which is alkalinity and pH, and how by adding different supplements will affect these two parameters accordingly. Alright, right, so I'll see you guys on the next chapter.